Professor Jansko, the floor is yours.
Thank you. Can you confirm that you can hear me and the screen is visible?
Yep.
All right, excellent. So good afternoon from Chicagoland. Let me just start by saying thank you for the opportunity to speak about this package for superconducting qubits here. scqubits is a project that my former postdoc, Peter Broszkowski, and I started in 2019. And it runs on all three major platforms, and it's completely open source. So if any of the following seems a bit like advertisement, then it is not because any of us is making money off of the software. We're not, but because I'm actually genuinely excited about how this package has made our own research more efficient, and I'd like to share that with you. We've just released version number 2 this past weekend with a number of added features and improvements, and we're delighted that over the course of this past year, we've accumulated a little bit more than 42,000 downloads on Conda. All right, so with this presentation, I would like to accomplish a couple of things. First, I'll say a few words about why we think this package is a good idea, and in that context, I will briefly touch upon some of the other packages that are available. Second, I will give an overview of scqubits so that there's a clear understanding of what is its scope and what is its range of functionality. Third, I'll describe how to quickly get started with the package, and then highlight with some examples what we think are some of the strengths of the library, and then outlook on future plans will conclude my talk. So why yet another package, given that there are others out there? I think you'll see in a moment that most of these packages kind of complement each other rather than compete. So let me start with PyPR. In fact, Zlatko Minev, who's one of the authors of this package, will speak both in this session at 3:48 as well as in a longer talk on Friday. And my limited understanding of PyPR is that it's a package that helps with circuit design as well as circuit quantization, and it interfaces with EM solvers such as HFSS. And it's particularly well suited for weak harmonic systems involving transmons, for instance. And I'm excited to learn, hopefully in the 2 talks, how well this works for something more anharmonic like fluxonium. QCAT is another package that works well for weakly anharmonic circuits, right? It actually uses the basis of normal modes by linearizing the Josephson nonlinearity in the circuits, and it produces energy spectra. It can predict some of the coherence rates, and it has a really nice graphical user interface actually displaying circuits. And that one comes out of the Steel Lab at Delft, and Mario Gelli is the author of that. And then the third package that I'd like to mention was authored by Andre Klotz and Lev Yoffe. Andre is giving a talk also in this session, and he must be a private person. I couldn't find an image of him, but you will see him live in a couple moments. I'm not sure that he'll actually be talking about this package, but it's a package that actually aims to describe and model arbitrary circuits, meaning that you specify your circuit and the package is going to find the right variables and set up a basis and hopefully give you the energy spectrum, where the hopefully, or this legal footnote here is that my understanding is that there's no magic anywhere in our packages, right? If the circuit becomes too large, then Hilbert space becomes too large, and eventually we just all run into memory bottlenecks. They're interesting games to play, but nothing that fully cures this problem. All right, so our library, what is it? Why were we motivated to invest time into this? So the first thing perhaps to mention is that in our own research on superconducting qubits, we just like everybody encounter certain tasks that we have to solve and do over and over again, right? We want to compute energy spectra, we want to visualize wave functions, calculate matrix elements. Those matrix elements then feed into our estimates for coherence times. Perhaps, and most likely, we want to model larger systems, composite systems consisting of multiple qubits coupled to harmonic modes. And for such systems, we probably want to be able to do parameter sweeps to kind of see what is the energy spectrum as a function of one parameter, perhaps multiple parameters. And then often we would like to actually be able to take such a composite system and to simulate the time dynamics. And QTIP, of course, is perfect for that, but there's this question of, how do we best translate what we have over here into the language that QTIP understands and allows us to just feed into MESOLVE, for instance. And then last but not least, there's also a question of how do we best store and share data, because Python pickling is not always the best portable and secure way to do that. And I think it is fair to say that all of these things already exist in various labs, in various languages, in various forms of code. But I think it's also fair to say that the way research goes, most of the time, once the project is finished, once your paper is about to be written, then you're probably not going to sit down and write documentation for your code. Many people won't. And likewise, it then sort of seems maybe luxury to make the code maintainable and extendable. And if the paper is written, why optimize the code further because it already worked, and why even think about interface and making this look nice? But we thought that it's actually worth the effort because otherwise, we find ourselves reinventing the wheel over and over with people writing the same code multiple times, and so we thought this would be a good idea. The other thing perhaps to mention is many of you are aware that funding agencies like DOE and others in the context of the National Quantum Initiative have been emphasizing that it is our responsibility to help and develop what you might call the quantum workforce, right? We need people who are willing and excited to work on quantum information science, and to make that work, right? Reaching a broader audience is an important thing. We need to try to make our research more accessible. I know that there's a number of institutions in the US, for instance, where kind of bringing modern quantum mechanics into classrooms has been successful. And I think that having tools at our fingertips, beginner-friendly tools that perhaps are appropriate for users who do not have a lot of programming knowledge, can be a nice asset in making all of this happen. All right, and so what is currently in this scqubits library that I'm somewhat advertising? So first of all, there's this new graphical user interface for beginners, and I'll show you a little bit of that. There's a number of superconducting qubits included and implemented. You see them over here. One of the newest additions is the cosine 2 phi qubit from Michel Duveray's group. And then the library is very good at computing and visualizing things that we need, right? Eigenenergies, wave functions, matrix elements, all of that. And then I'm going in the wrong direction, but here are the more advanced components of the library. So as I said, we would like to build up composite systems consisting of multiple qubits and oscillators coupled to each other. We have now a much more flexible way to let the user actually put in the interaction terms, and overall this then has a very simple interface to QTIP, as you will see. The submodule of the library that deals with coherence times was entirely written by Peter Gruszkowski, and it beautifully estimates depolarization and dephasing times. In fact, considers various common noise channels for the individual qubits. And it does have defaults for noise amplitudes and Q factors from the recent literature. But it is very flexible and allows the user to actually modify these defaults, put in a different temperature, define a different frequency dependence of the Q factor if needed, and kind of tailor everything towards the specific application. The parameter sweeps are partially new, so we now have support for multi-parameter scans, and I will illustrate that in a couple moments as well. And there's now better support for creating transition energy plots that should be and can be directly compared to experimental two-tone spectroscopy. And most of this has multi-core support, right? Our CPUs these days typically have multiple cores, and harnessing that is a good idea. And I'm not going to talk much about the file input output, even though I think it's a neat part of the library. All right, so I think we've made the process of getting familiar with this package as simple as possible, and a good starting point is this documentation, which you can access through the shortened URL tiny.cc/qubit. And so we're going to try and play these recorded screencasts. So we'll jump over there, and this is what the documentation looks like. The first section has information on how to install the library through Conda or pip, so that's straightforward. And then there's an extensive user guide, starting with basics, illustrating things with examples. Down here are some of the more advanced topics. Up here is a list of the qubits that are implemented, and I think we're going to jump into Fluxonium rather, to just for an example. So here's up there is the model, right? There's a short description of what the numerical implementation is, how to make an instance of the qubit, and then you have some of the summary of the methods that are of interest when working with this qubit. So for instance, get an eigensystem and such. And beyond this user guide, we have a number of Jupyter Notebook examples. Those can be accessed through Binder, which is neat because it actually gives you a live online notebook. If you don't want to immediately install scqubits, then you can play with it online without that overhead. And so I think the plan is that we just jump into a notebook so that I can show you what the graphical user interface for beginners actually looks like. So we'll just import the library as you usually would, and then there's a simple command that calls for the display of this graphical user interface. And I'll have to zoom out here a little bit so that we can see the whole thing, indeed. And so we'll switch to wave functions for the first step here. And over there, you see qubits, right? There are a number of familiar faces like Transmon or Fluxonium, and some of the more advanced or next generation qubits that are part of research like 0pi or cosine 2 phi. And they all come with a little info box that you can activate, and then you see the Hamiltonian definition of parameters, the circuit that underlies all of this, and in most cases, sort of a sample device image. And that goes through for the other qubits as well. Let's see whether I can get this video back working. There we go. So clicking on Fluxonium brings up information on that, and so on. And finally, cosine 2 phi. So I'm going to go back to Fluxonium and get rid of this info box and actually see a little bit what is down there, right? So you have the plot of the wave functions for Fluxonium, right? There's the Fluxonium potential, low-lying wave functions vertically offset according to their eigenenergies, just as you're used to from typical textbook images for the harmonic oscillator. And then if we look at the panel above here, you see that there's qubit parameters that you can modify, as well as things about the display. So we could choose, for instance, to add a couple more wave functions, maybe number 8 and 7, right? And they pop up here and are visible. Great. You could choose to display the mod square of the wave functions instead of the real part, and that works. I like the real part better, actually. And then you can go over there and change the charging energy, change the inductive energy. You can play a little bit with the external flux and see what happens when you ramp that across certain values. And you see how the wave functions adapt and the potential changes. Okay, similar for the energy spectrum, so we can plot that as a function of actually various external parameters. This is still flux. You could choose something different. The spectrum looks perhaps slightly unfamiliar for experimentalists because I did not choose to subtract the ground state energy, but if you prefer to do that, you can. And again, changing qubit parameters obviously will change what that spectrum looks like. Matrix elements are important as well. You can pick among the different operators that this qubit comes with. So let's do phi operator for fluxonium, right? And then for people who are color impaired like myself, it's actually neat that you can overlay this with the actual values. That's very helpful. You can also display matrix elements as a function of an external parameter. Those are actually interesting, and it's sort of a fun game to see whether you have enough intuition to predict what should happen, because these can actually change quite a bit depending on parameters, as you can see here. All right, and then let's switch back to wave functions once more and go over to 0 pi. So that is now a qubit with more than 1 degree of freedom, right? So it's 2, the wave function is 2-dimensional, and just really quickly, right, why is this thing called 0 pi? It's because the ground state wave function is localized along theta equals 0. And then if we go to the first excited state, then that one is localized along theta equals pi. And then there are higher wave functions with different physics that is actually important for gate operations on 0 pi. So that's this graphical user interface, which is, I think, indeed appropriate for beginners. I like to play with it as well. From here, I'd like to kind of progress to somewhat more, perhaps, interesting examples. So one thing I would like to show is a very basic usage of getting coherence times for a qubit. So let's see whether this works as intended. So I'm going to just define a tunable transmon qubit. It brings up this GUI. If you don't like GUIs, you can do it without. You can change the parameter values and then just perhaps ask for the eigenenergies as a function of flux over some range that you define. And again, the spectrum looks somewhat funny because it shows the flux-dependent ground state energy. We can quickly change that by subtracting that out, and then you get something that might look a little bit more familiar. Real quick, one remark, you see this gibberish here, perhaps, which is actually meant to be there in that all the plot methods hand you back matplotlib figure and axes, which is meant to help you actually get these figures into the kind of shape that you like in a publication. Some of the options for matplotlib are actually directly accessible, and you can just stick them into those methods. So you could say line width should be larger, and it'll happily do that for you. All right, but let's take a look at coherence time. So each qubit comes with a number of supported noise channels. This tunable transmon has 3 dephasing channels with 1/f flux noise, critical current noise, and charge noise. And then there's depolarization with capacitive loss through the flux bias line. And then this last one is only going to be important if you choose to couple your transmon directly to a semi-infinite transmission line, which most of us wouldn't do. But it's sort of neat that what Peter made happen here is that you can basically just get an overview of over all of these channels. So we'll take a look again at the behavior as a function of flux. And indeed, you see that you get a number of plots here. The first 3 showing the dephasing contributions from the 3 channels I mentioned, and then likewise for the depolarization. Great. And it's clear that there are further methods that allow you now to combine this and add up the rates and get effective T1s and T2s. I'm not going to show that because I'm eventually going to run out of time if I show everything. All right, and then as the last piece, I would like to illustrate a little bit how we build up composite systems, how the library interfaces with QTIP, which I think is important to many of us, and then how to perform multidimensional parameter sweeps. And so what I have in mind is to build up a system of 3 components. Let's do a tunable transmon qubit. We can shuffle around parameters here a little bit. And then I think the second component I chose is a fluxonium qubit. Let's see whether I remember that right. There we go, indeed. And both of these qubits then are going to get capacitively coupled to a resonator or oscillator of some kind. So we'll create that as well. And now we have all the 3 subsystems together. This truncated dimension that I'm editing everywhere basically says that once you've diagonalized each subsystem separately, how many of those eigenstates are you going to forward into the joint Hilbert space? So I'm limiting that to not make my Hilbert space too large. And then we're going to just combine all of this into a Hilbert space object that also has a little graphical user interface. Again, not all of us like those. You can do all of this programmatically without ever invoking graphical user interfaces. But here, so we'll do it this way. We're selecting the subsystems that are supposed to be part of the Hilbert space. And then we're going to create interaction terms, which are, I'm just going to capacitively couple each qubit to that same oscillator through their charge operators, and then A plus A dagger for the oscillator. So let's see how that works. You select the transmon, you say it's the charge operator, it couples to the resonator, and I'm just leaving the annihilation operator there because we can add the Hermitian conjugates, so that's sufficient in this case. And then we'll just rinse and repeat, do the same thing for fluxonium, and couple to the resonator with some different coupling strength. There we go. All right, and then we create that Hilbert space object, and we can convince ourselves that indeed everything is in the right place. So we can do a quick print of that, and you see, oops, that was unfortunate. This is the problem of doing videos. There we go. So this is the printout up there, and you will have seen hopefully that there's the transmon up there, fluxonium oscillator as intended, and the 2 interaction terms. And the next thing that has already come up here now is I wanted to show, you can now call the for the Hamiltonian of this coupled system. It's very simple, and it'll generate output that looks like that. And to some of you, I hope that this format of output actually looks familiar. So indeed, your suspicion is going to be confirmed if you ask, what is the type of this object actually. So we'll just stuff in the full Hamiltonian there. It will say that indeed what is being handed back is a Q object, which is from the QTIP package, and is exactly the kind of thing that you would then take and directly stick into something like MESOLVE to solve the master equation. Probably you would like to add a drive term to make things interesting. But scqubits does all the job of creating the correct tensor product of operators that have to be wrapped with identities from the other subsystems. So all of that is taken care of and can go directly into QTIP. You can, of course, directly get the eigensystem of the interacting system here. They're the eigenvalues, QTIP eigenstates. And then let's see what we can do about a multidimensional parameter sweep. So what I had in mind here is, both the tunable transmon as well as our fluxonium qubit, they have loops, so we can feed in magnetic fluxes. I'm imagining something like flux bias lines, so there will be 2 independent fluxes, flux 1 and flux 2. I'll sweep them over the same range from -0.6 to 0.6 flux quanta. And in this little toy model, I'll introduce a little bit of crosstalk between the 2 of them. So I'm collecting names of of parameters and values, and then we'll define this function that allows us to specify how do those two. Oh, this is unfortunate with this video. I apologize. Jump back to the right place here. So we'll let flux 1 mostly affect transmon, our tunable transmon. Flux 2 is the predominant source of flux in the fluxonium, and then there's a little bit of crosstalk from the opposite flux. And once you've set all of this up, you provide all of that information to the parameter sweep. You specify, how many cores you want to use, and right now it would actually be calculating. And I've sort of tried to cut this short, obviously, by doing a recording of this, so you don't have to wait. And now that it's done, it's very easy to interact with the data that have been generated. So all of the bare eigenstates and eigenvalues are now stored, as well as the dressed eigenstates and eigenvalues. And so if you call for the dressed eigenvalues, what you get back is a bunch of numbers, and it looks like a NumPy array. It has a slightly different name because we decided to subclass NumPy arrays and actually make things work a little bit more easily for you. So let me try and show you that, well, at the bottom of this is a NumPy array, so you can get the shape of this. Remember, there were 2 parameters, both have 99 values for the 2 fluxes. There are 20 eigenvalues, but alongside with that information is stored the names of those parameters on the first two axes and the values, which is really nice because you can now actually, instead of referring to those values by their indices 2 and 15, you can first of all you can say that let's grab we'll specify flux 1 and we'll grab index 5, and so it recognizes the name of the parameter. It does this name-based slicing. But we can also do value-based slicing, along with the name. So, this 0.3 flux value may not have been an exact entry in your original choice of values, but it grabs the closest one and then allows you to do the slicing of your array that way. So all of that is just meant to make your life simpler in working with the large amount of data that actually gets generated by these parameter sweeps. And I said that now that we have all the eigenvalues, eigenenergies generated, it's very easy to actually say, let's fix flux 1 at value 0.2 and plot the transitions in our system. So those are all differences between eigenenergies. And you see that we're coloring some of them. Those are transitions among just within each subsystem. So this coloring works very well as long as the system is sufficiently dispersive. You see all the transitions start in the ground state. The first one here goes from the ground state to the first excited state in subsystem 1, which should have been the tunable transmon, I guess. And then there are other labels. So the ones back here are the ones for the resonator. Those are the ones for the resonator, I believe. And so there are various options to work with here. I have to watch the time a little bit, but I hope our chair is going to give me a warning if I run late.
I have 2 minutes left.
I have 2 minutes left. Thank you very much. So you could specify that you only want to see transitions for the fluxonium subsystem, and it does that for you. You can actually also include sidebands, which is going to mark more of these transitions. And let's see, I think that's what I had in mind there. Yeah, so you see that now you see a bunch more. There's an option to say that, well, if you're dealing with thermal excitations, you might have to start out in a different initial state. And I think I had an example for that, which comes a little bit later. But I'm probably going to cut this short. You've already gotten a flavor of the things that you can do. This is now just showing transmon and resonator transitions. And I think the initial state being an excited state comes here as the very last example. If we give it one more second, there we go. and then it will do the subtractions to account for the excited state being the original, the origin of your transitions. All right. There's much more, so I didn't get to show that you can do custom sweeps, right? You can provide a user-defined function for something that you want to calculate versus these parameters. You could, for instance, choose to calculate T1 of a qubit as a function of circuit parameters and or fields, and then feed that data into an optimizer very quickly. We are calculating things like lamp shifts, Stark shifts, and Kerrs already. And there's a very easy lookup to switch back and forth between labeling states by their address state indices versus bare product state labels. Outlook of what might come next. So we are definitely going to add the current mirror qubit to the library along with this variational tight binding method that my graduate student Daniel Weiss will be talking about on Friday. And then qubits we're really interested in, like the Snailmon and the bifluxon qubit, should make it into this package as well very soon. And then down the road, thinking about including drives and Floquet qubits would be fun. And then I've been working a little bit on a prototype app that would harness scqubits to actually display experimental two-tone spectroscopy data, allow you to extract data points, do fitting, and then overlay this with the actual scqubits fit. I would like to thank all of the people that were involved in this project. I hope that some of you might consider to contribute, perhaps just by filing issues if you encounter them. I would like to thank the Air Force for giving us money to continue this work. And I'll just finish with this slide and thank you for your attention.